Hey, I'm supposed to post midterm grades today. I know we've only taken one exam, but it'll be based on where you stand right now. Even though there's another, our exam's next week. So it's not a good indication of where you are until after next week, but I'm required to have it done today. So just FYI, you might get something that says, hey, your midterm grade is this. I don't know if they send you an email or not, but. I'm using the alternative notation, right, for this right here. That could have been written this way. Same notation, right? So just make sure you're aware of that. So what are we going to do here to get this derivative? What do you have going on? Product rule. Good. You got a product right here. Now the first part of that product rule is going to be pretty straightforward, right? Derivative of x, and then times this. Then plus, when we do derivative of the right side, chain, right? You got natural log. Inside that, you got arctan. Let's see if we can knock this out. Y prime should equal 1 times natural log of, I've never liked writing arctan. I've always preferred that. That's just me, my personal preference. What now? Plus derivative of natural log of something. 1 over arctangent x, and then times the derivative of arctangent x, right? 1 over 1 plus x squared. Am I done? Times the derivative of what's inside arctangent. What's the derivative of this? 1, so there's really a 1 here. I don't need to write it. Then finish off the product rule, x. So this was like our f prime g plus g prime f. Like g prime is all of this right here. Everyone see it? As far as cleaning up, there's not a whole lot more you can do with this. You know, you can put this x on top of this, but don't do this. Look, very, very dangerous here. That is not tan x, okay? That's one bad thing about this notation. We've always been taught that if you have a negative exponent, you can bring it up, or if it's on top, you can bring it down. This negative 1 does not mean raised to the negative 1 power. It means it's the inverse function. So it's kind of bad notation in math, so be careful with that. All right, that's pretty much it for the derivatives of inverse trig functions. Double check your homework assignment on this. There's some stuff in the beginning of this homework assignment that I'm a little concerned about. Let me see. 3.5. I'll do one of these. These are going to come up in your homework, but this is not a Cal 1 topic, but I may as well do one. So in your homework, they're going to ask you a problem like this, like find secant inverse of 2. No derivative. So this is just pre-cal. So if you need to, this is why I drew these pictures earlier. You know, if you've got something like this, if this is secant x, right? Then arc secant goes back. Agreed? And what you're trying to do is you're trying to figure out, when you plug 2 into this, right, where 2 goes. So your answer is going to be an angle, isn't it? So another way to look at this would be to ask yourself, what angle do I plug in to secant that spits out 2. Maybe it'll be helpful if you remember that secant is 1 over cosine. So what would I plug in? What would I plug in here? What would I plug in for x that when I plug it in right here and do 1 divided by that, whatever that angle is, I get a 2. I'll give you a hint. It's one of the common angles. What is it? What did you say? Pi over 3. So let me see. At pi over 3 on the unit circle, you're up here, right? The point on the unit circle there is 1/2 root 3 over 2. Or the other way around. Sorry. No, 1/2 root 3 over 2, but is that the one we want? That's pi over 3. This one. Well, no, I'm just want to make sure you understand the difference between the two, right? This is pi over 6, pi over 3. What is it that we're looking for? We want cosine of some angle to spit out a what down here?
2.
Well, 2 in the whole thing, right? But what down here would give me 2? A 1/2 here? If this was 1/2, 1 over 1/2 is 2. So when you're on the unit circle, which of these coordinates corresponds to cosine? The x-coordinate or the y-coordinate?
Yes.
The x-coordinate. So what I'm trying to do is find on the unit circle somewhere where my x-coordinate is 1/2. And what angle is that? Pi over 3. This is the angle pi over 3. Yeah? So the answer here should be pi over 3. You have to understand all this stuff, okay? I mean, this is pre-cal. You're going to go back and review. But they want you to do that because it's useful. Yes?
Isn't there another way to do it? Everyone was doing it algebraically before.
Well, you could do it algebraically like this. You could say, all right, what is secant inverse of 2 equals, let's just call this answer x, okay? Then you could take secant of both sides, right? Then secant of secant inverse would be 2. So secant x is 2, right? But then what's secant? Secant is 1 over cosine of x, right? And then multiply both sides by cosine x. You get 2 cosine x equals 1, but then cosine x is 1/2. I don't know if that's what you're talking about, but here's the problem I have with this, is that everyone, if you're going to do Cal 1, Cal 2, everyone should have a very intimate relationship with the unit circle, okay? Like engagement ring, wedding ring, like we were talking about earlier. I mean, you should be really close to this thing. You should understand it. You should understand how it works. And so when someone is saying secant inverse of 2, you should automatically be thinking, okay, I need to figure out, secant has cosine in it. Which cosine things in here give me 2's? Well, 1/2 is the reciprocal of 2. So, I mean, that's how it should be instead of algebraic. Because honestly, in a Cal 2 class, you don't want to sit there and set this up and go through all that work when it should just be like a little 15-second exercise in this mentally. Do you have another perspective?
Isn't there like another angle?
I was going to ask you about that. You mean this one around down here?
Yeah.
Wouldn't that angle give me the same x-coordinate? So, that's right. We're dealing with an inverse trig function here. And they have domain restrictions. And in particular, secant inverse is restricted. And you're not allowed to look at the bottom 2 quadrants. You're only allowed to look between 0 and pi, which is exactly why they do it, because you would have more than one answer. And that would be, the horizontal line test. You're basically hitting in 2 places. So you throw out the ones that you need to so that you only hit in one place. I'm glad you asked that, because I was going to show it to you, then I forgot, and then you reminded me. So thank you. All right. So when you get to the first 6 problems in your homework, just realize that it's this stuff. And then I think numbers 16 through 27, that's all derivative stuff. All right? So I don't want you to be caught off guard like, he didn't show us that in class. it's going to be pre-cal. All right, we're ready to move on. We've got another 25 minutes. Can you all hang? It's Monday. I know it's Monday. It feels like Monday, but let's get this sign-in sheet passed around at least.
So we're moving on to 3.7.
Yes, we are moving on to the Big Daddy, LHospitals. Today's the 19th. Please sign in on the 19th. Don't worry if you signed on the wrong column last time. Just sign on the 19th. Okay. We are doing 3.7. These are the two topics for this section, all right? And what I'm going to do is I'm going to start, and let's just put a big old asterisk on everything here. This is such an important section in this book. This is a lifesaver in a lot of different classes that involve limits. This rule in understanding indeterminate forms, if you got this down, you save yourself a lot of time. I gave a Cal 2 test last week. And my last two problems on the test required that the students use LHospitals' rule, and that there were two different types of indeterminate forms in those problems. And I think that on one of them, only 2 students got the question right, only 2. And it was because we had talked about LHospitals' rule in class, but I didn't cover LHospitals' rule. Like, I didn't go through and explain what it was. I just assumed they had seen it in Cal 1, so a lot of them really struggled with it. And they even told me, like, I don't remember LHospitals' rule. I'm not comfortable with it. So that's why I want to spend as much time as we can on it. All right? All right. Let's first talk about indeterminate forms, then we'll get over to LHospitals' rule. All of this, everything that I'm referring to right here, falls back into the idea when we were talking about the limit that started this whole class off. Remember, we did limits, right? Okay, when we did a limit, something like this, limit x approaches 2 of x squared minus 4. And I know how much you all love the limits. You know, like a lot of you sent me emails, wrote me little letters, and left them in my office. Please, more limits in this class. Please, more limits, right? No. They were a struggle, right? Some of these got pretty messy. Let's look at this. This is one of the most basic first limits we ever investigated. So what happens as x approaches 2? The top, I used to do this thing, right? 0 over 0, right? That's what we would write. And I wrote an arrow because I didn't want to say it was equal to 0 over 0, because we're not plugging in 2, right? The limit is saying what happens as you approach 2. If we approach 2, the top approaches 0, and this approaches 0. So this little arrow, you know, really indicates that we are approaching. We are approaching this, right? So this right here, 0 over 0, is what we call an indeterminate form. It is a form of a ratio, in this case, that we can't determine what the answer is just by looking at 0 over 0. It's indeterminate. Now, if we were back a couple of, month ago, 2 months ago, whatever it was, how would we have handled this problem? We would do some sort of factoring, right? On the top, we would do difference of squares, and we would notice that a factor cancels. And now when we take the limit, we don't get this form anymore, do we? We just get straight away 4, right? So our answer to this form before was to do some sort of algebra or some sort of trick, right? I even gave you a sheet, right, that showed what to do. So when it comes to indeterminate forms, all right, we'll get to L'Hopital in a second. When it comes to indeterminate forms, the first type of indeterminate form that we have is 0 over 0. That is an indeterminate form. What other situations did we run into here where we couldn't tell right away what the answer was? Okay, so hold on. I'm going to write down what y'all are saying, then let's talk about them. I heard fixed over 0. Was that indeterminate? What were the possibilities when we had fixed over 0? Does not exist, or infinity, or negative infinity, right? Okay, with this type, this is not what we would consider indeterminate, because we know the answer is going to be really one of two things. It's infinity or negative infinity. Let's count that as one thing, right? Infinity or negative infinity. That's basically infinity. Or it doesn't exist. I mean, it's not like it could be anything. Where like here, we could get like the answer could be 4, the answer could be 10, the answer could be negative pi. There's so many different things it could be. Here, it's really kind of, we got it cornered, don't we? We know it's one of kind of a few things, that's all. So that's not an indeterminate form. Keep going. What else? What? You're ahead of me, yes. Can I do this one first? This one? Remember getting that? We get infinity over infinity, and we say, I don't know. I'll give you an example of one of those. And then maybe you can remind me how we did this. Top goes to infinity, bottom goes to infinity. Anyone remember how we would do that?
Yeah, we factor it out.
Divide by the highest power of x on the bottom, and you get some of these to go to 0, squash down to nothing, right? So that's how we would handle it. But there were times where this could turn out to be a number. It could go to 0. It could go to infinity. There's so many things it could have been. This is also an indeterminate form. We need to do something more than just looking at it to figure that out. We don't have it narrowed down. The next one I heard was infinity minus infinity. Is that an indeterminate form? What do you think? If something is getting really, really big, and you take away something that's getting really, really big, can you tell me that it's 0? You don't know how big they're getting, how fast, right? So this right here is also something that we don't know. Sometimes it is 0. Sometimes it becomes infinite. Sometimes it becomes negative infinite. Sometimes it's something else. So that is also an indeterminate form, all right? What others? Can't really think of anything else? How about this? How about infinity? How about fixed over infinity? That's 0, isn't it? That's not indeterminate. We know that that's going to 0, right? So that's not on our list of indeterminate forms. Infinity over 0? I don't remember us looking at that. What does a fixed number over infinity want to do? If that was fixed. If a denominator gets smaller, what does the ratio do? It gets bigger, doesn't it? Let me write it this way. I don't know if that makes any sense to you, but that's the same kind of idea as this, isn't it? This one right here wants to become what? Bigger or smaller?
Small. Or bigger.
This ratio wants to get big, doesn't it? This one?
Small.
Infinity over 1. It gets big, doesn't it? Let a number get big, 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 and then the bottom's 1. Isn't that a big number? This is a big number, and this one right here is wanting to also get big, isn't it? What's big number times big number? Big number. So that's going to be infinite. There's no head scratching there. Does that make sense?
What about infinity times 0?
So this is not an indeterminate form. Is that all right? That's blowing up. It's getting huge. What about what?
Infinity times 0?
Ah, Okay, infinity times 0. What's happening there? You know what?
We'll just go to 0. So then-
You have a number that's getting huge times a number that's getting small. Can you tell me what's going to happen there? You don't know how big that is, right? You don't know how small that's getting? Look, I'm not saying the number 0, okay? I'm saying it's getting closer to 0. I'll give you an example of this. Limit x goes to infinity of x sine of 1 over x. Okay, where does this go? That goes to infinity. What's 1 over infinity get close to? 0. What's sine of 0? 0. So this is getting big, right? And this one is getting small. Which one wins? You don't know. You have to go figure this out. We'll actually be able to do this pretty easily in a second. But this one we don't know. Okay? So that is also an indeterminate form. Please, I can't stress this enough. When I write infinity times 0 on the board, infinity we know is not a number, right? It's an idea. 0 here, I'm not saying the number 0. I'm saying if something is getting really, really small. So these are like, when I take the limit, it's going to 0, going to infinity. What else? Would infinity times infinity, we already talked about that one? Is that indeterminate? I think we did talk about that, right? Big times big, that's still big? How about big plus big? Still big? So those aren't problems? Those aren't indeterminate? All right, how about some things we haven't looked at? Okay, what about e to the infinity? Or 4 to the infinity? Or 10 to the infinity? Those are all becoming infinite, aren't they? E to a bigger power gets bigger. So all those blow up. So that's not indeterminate. Okay, how about this? This we've never looked at before. Something that has this form. And I'll give you an example. Limit x goes to 0 of x to the x. Now, why is this an indeterminate form? Well, you've been told in the past that 0 raised to any power should be 0, right? But you've also been told that anything to the 0 power should be 1. So what is it, 0 or 1? Or something else? Do you see the problem? So with a problem like this, we don't know. We have to actually go do something with this. So that goes into our list. Understand? I want you, more than anything, I want you to understand why it's going to our list. I don't want you to just be like, any freaking thing you can think of is on our list, like this. Like, is that on our list of indeterminate forms? Why not? What is that headed towards? The exponent's headed to infinity. I agree with that. No, but that's not the number 0. It's going to 0, right? So give me an example of a number that's getting really close to 0. 0.1, 0.01. Okay, so as an example, how about like 1/100th? Is that a number that's getting small? Now, I would like for you to raise that to a number that's getting big. How about 200? What happens? This gets smaller, right? What happens when you take this 1 over 100 times itself, times itself, times itself, times itself? Isn't that what happens when you take small numbers and raise them to powers? They get smaller? Everyone has this idea that when you square a number, it gets bigger, right? Oh, you square a number, it gets bigger. No, not if you take 1/2. You square 1/2, you get 1/4, right? That didn't get bigger, that got smaller. So if you take a small number, it's trying to be small, right? And this one's sitting there going, I'm going to help you get there, because I'm going to make you get there faster. Does that make sense? This is not an indeterminate form. That's going to 0. There's no question. You got it? So we don't want to start throwing everything we can think of over here on this list. It has to be something we can't determine. That's not it. That's not one of them. Can someone give me an example of one that would be on our list?
Bounded would be, right?
Bounded what? I would have to have a specific example of what you're thinking. Look, I just put 0 to the infinity, right? And it didn't work. Flip it. Would that be on our list?
Yes.
Yes? Why? What does the base want to do? What is this base trying to do? Get huge, right? Big, 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 big. What is the exponent trying to do?
It's small.
It's trying to get smaller, but it's also saying that anything raised to the 0 should be what? 1. So the exponent's sitting up there going, I want to turn you into 1, right? And the base is looking like, no, I want to be big, right? And they're fighting each other, you know? Does that make sense? Maybe you don't need them to actually visualize them talking to each other, but that's the way I always looked at it. Like anything to 0 wants to make the whole thing 1. And the base is just like, no, I want to be big. And they keep fighting and you can't determine what happens. Anything else? 1 to the infinity. Now again, remember, I'm not saying the number 1. I'm saying the base is trying to become 1, right? So we already said 1 to any power should be 1. That's if it's exactly 1, right? 1 to any power should be 1. But if I take a number that's a little bit bigger than 1, and I raise it to this huge, ginormous power, right? 1 million, 2 billion, whatever, is that number going to get bigger or smaller? It's going to get bigger, isn't it? It's going to get bigger, because it's a little bit bigger than 1, isn't it? So it'll get a little bigger as I multiply through. So here, the base is like, I am here to make you blow up, and the base is like, I just need 1, and 1 to any power is 1. And so they're not happy. Good. Any others? Zero to the 0 we got. Infinity to the 0 we got. Now, didn't I give you a handout once that had all the indeterminate forms on it? Did it have them on there? Who has it? I know Jared probably has it. Is it? Let me see. Does it have them on there? Yeah, right there. This form, this sheet right here, top left-hand corner, it gave you all the limit forms. And those limit forms should include everything on this list. Right? That's all of them. So these are the types of limits that we can face that we have to do some work on, right? We have to do some work on. We've seen from the past that that work can be pretty involved. And then along comes L'Hopital. L'Hopital, mathematician, came up with this wonderful rule. It's spelt LHospital, but it's pronounced, I've heard different pronunciations, but I've heard it's L'Hopital. So here's the rule. It says this. Suppose you're taking a limit, and it really doesn't even matter what the variable is, and it doesn't matter what it's going to, but you have two functions. I'll say a function of x on top and a function of g on the bottom. So you have a ratio of two functions. Suppose that you have this limit, and you're getting on this infinity, 0 over 0 or infinity over infinity. So L'Hopital is saying, hey, you're trying to take a limit, you're getting this or this. And also, this doesn't matter if it's plus or minus, okay? It does not matter there, plus or minus. Because you can always pull a negative out of a limit and it doesn't affect anything. So L'Hopital says, if you have any of these two, here's something you can do. Now, does L'Hopital address all these others? No, just these two, right? But that's okay, we'll have a way around that. That's the way the rule starts. Suppose that you've got this bad situation happening. Then, if the limit, as who cares approaches who cares, of f prime of x over g prime of x equals L. Then I'm running out of space because I wrote so big. Then the limit as who cares approaches who cares of f of x over g of x equals L. So let's try and interpret what this very, very powerful rule tells us. You got a limit, you're scratching your head, right? You're like, I'm getting 0 over 0, I'm getting infinity over infinity, I can't figure out what the answer is, right? L'Hopital says, okay, fine, you having some trouble? Take the derivative of the top and the bottom separately. Not quotient rule, just derivative of top and bottom separately. Look at that limit. If that limit turns out to be a number, that answer is actually the answer to the original limit. That's the rule. And I'm not here to prove it to you. It's quite an involved proof. Not one of the easier proofs to do. So, super powerful. Let's see how this works. All right? Just remember you have to have one of these forms. If you don't have these two forms, you've got to do something else. So let's go back to that one that we all started class with. It was this one, like limit, or x approaches 2, x squared minus 4 over x minus 2. And we all had agreed that we had the correct form, didn't we? We have 0 over 0. Now, Justin said, hey, just factor the top, cancel. We got an answer of 4, didn't we? But let's say we didn't know how to do that. According to L'Hopital, if I take the derivative of the top and bottom separately, apply the limit again, if I get an answer, that answer is the answer to the original problem. So our standard way of doing this is to let everybody know right now that I'm about to apply L'Hopital's rule. So I'm going to take the derivative of bottom and top and bottom separately, right? To do that, most textbooks will put an H above the equal sign, or an H and they'll circle it, and that's for L'Hopital. Oh, I erased it. Or for me, and I don't know where I did this, I just wrote an L there to let people know I'm doing L'Hopital's rule. No matter how you do it, H, L, whatever, just indicate to the reader, to the person looking at your work, that you're applying the rule. And that's all you have to do to let people know. So you'll rewrite limit, x approaches 2, but thank you. But instead of writing x squared minus 4, I'm going to write what? The derivative of the top, 2x, over, what's the derivative of the bottom? 1. And now try and plug in the limit now. What do you get? 4. Wasn't that nice? Wasn't that nice? Oh, Justin asked the question. Yes, he did. I'll get to that answer in a second, Justin. Okay, let's try another one. Do you remember this? Limit x approaches 0, sine x over x. Anybody remember what that limit is? It's 1. Why is it 1? Because I told you it was 1, right? Didn't I tell you it was 1? I said, if you want me to show that to you, come to my office. It involves a special proof using triangles and circles, and it's very complicated, the proof. But I also told you that later on I'll be able to show you it's 1 very easily. Well, today's the day. Because when we do it, we can see that we get the form of 0 over 0, right? And so because of that, I can apply L'Hopital's rule. And I'll come in here. I'm always going to do L's. Sorry. Derivative of the top, cosine x. Derivative of the bottom, 1. Now, let x go to 0. What's cosine of 0? It's 1. So there. That's it. You have to believe L'Hopital's rule for that, though. What are y'all thinking? Y'all are having the same reaction that all my classes have when I show them this. Yeah, I should have started with this, right? Have you ever heard the expression, don't get the horse in front of the carriage? Okay, now think through this for a second. Don't get the carriage in front of the horse. Yeah, I got that backwards, right? Okay, don't get the carriage in front of the horse. Look, if you look at the evolution of what we've learned in this class today, this semester, we started out with the limit, right? From the limit, we said limits could be used to actually define this thing called f prime of x. F prime of x actually happened to be a limit, didn't it? It was a limit, h approaches 0, f of x minus f of h over x minus h, or sorry, f of x minus, f of x plus h minus f of x over h, bah, right? And then we went and we did what? Implicit differentiation, related rates, and all these different things, right? And now we're here and we're like, oh, L'Hopital. And we're like, ha, 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 you know, you can use this to use limits, or to do limits, right? Why couldn't I show this to you before, in the very beginning of class?
Because we didn't do all that middle jump.
Because, well, but what do you need to be able to do L'Hopital's rule? A derivative. So if I would have walked in and been like, okay, everybody, sine x over x, that's simple. Take derivative of top and bottom. You'd be like, what the hell's a derivative, right? Right? So it's simple now because we have the derivative, but I couldn't have shown this to you before the derivative. That's why. Is that good justification? Okay, good. Because I agree. Now that we have it, it's great. All right, how about this? Do you remember these? God, these, you loved these. Limit x goes to 0. Again, I had emails. My box was overfilling with emails for special requests for more of these problems on tests. Do you remember this one? This is the one where you had to peel it apart and you had to like find hidden things and slide over and make it go turn into what you wanted to turn into. Yeah, like, yeah. But let's just check it real quick. Let x go to 0. Where does the top go? 0. The bottom goes to tangent of, let's see, that's 0. Tangent of 0 is also 0, right? And so you have 0 over 0. So you are free now to apply L'Hopital's rule if you wish. Do you wish to? Yes. Of course. So by L'Hopital's rule, you get the limit as x goes to 0. You have to take the derivative of the top. Cosine pi x times, hold on, cosine pi x times pi, good, chain rule. Don't forget, you have to take derivative of what's inside. Now that's separate, I'm done with derivative on top, derivative on the bottom. Derivative of tangent of something. Secant squared of 4x times derivative of the inside, 4. Now try it. What is cosine of 0? 1. 1 times pi? Pi. So the top is going to pi. Over. Okay, what is secant of 0? Secant of 0 is the same as 1 over cosine of 0. Cosine of 0 is 1. 1 over 1. So this is 1. Right? This piece right here is 1. Then you square it. 1. And then times 4. Pi over 4. Done. Oh, wait. Ooh, how did that happen? Wow. I'm out of time. Guess we were having too much fun. All right, so I won't say that you need to really do anything from 3.7. We will pick up on 3.7. Where's the sign-in sheet? Anybody need to sign in? Let me see where I am as far as class lectures are concerned. We're there, okay? We were supposed to start L'Hopital's rule today. So I am actually caught up.
Except for Wednesday, there's no class. Not
Next,
tomorrow, but
yeah,
next Wednesday.
the next one, right? We have no class next Wednesday. Our test is a week from today.
Yes.
And then we have no class on the 28th of next week. It's a faculty development day. They're going to take us and develop us, I guess. I don't know what they're going to do with us. So that means the next time we meet is the last time we'll be able to talk about the exam, right?
Yep.
I think I'm going to give you for this test some basic stuff on L'Hopital's rule, like things that are like 0 over 0, infinity over infinity. But you know how we had all those other ones? Those take some time, and I might just hold off on this test. I'll talk about it next class, but I don't think I'll put it on the test. That'll give you some time to do some practice homework. Okay? Everybody, I guess we'll see you on Wednesday.
So,
Turn this off.
l'hôpital rule is not in the test.